So in Unit 3, we learned about direct variation. So you know that has to go through 0, 0, because if you have none of one thing, you have none of the other. If your input doubles, your output doubles. If your input triples, your output triples. What we're going to learn about today is something called inverse variation. So the opposite is going to happen. So we're going to think if one quantity increases, the other is going to decrease as a result. So the inverse is happening. So we're going to look with specific modes of transportation. So if you think about driving and the time it takes for you to travel, we're going to make a 40-mile trip and we're going to have a bunch of different speeds. So if you think as you increase your speed, you're going faster, your actual time to go that distance is going to decrease. So there's a different relationship going on. So we're going to make a 40-mile trip. And if we just mosey down the road, we're going to go 1 mile per hour. We've got to go 40 miles. So it's going to take me 40 hours to make this trip. Now, if I start walking at a quicker pace, I can go 3 miles per hour. And I want to go 40 miles. So remember that formula we had, the distance is equal to the rate times time. So if we want the time, it's going to equal the distance over the rate. So in our instance, the distance is always going to be 40 miles, and the rate is going to be whatever our speed is. So if we're moving at 3 miles per hour, the time it's going to take is 40 over 3. It will take us 13.3 hours to make the trip. If we're jogging, we can go 5 miles per hour. So we'll do 40 over 5. And it's going to take us 8 hours. To bike, we go 10 miles per hour. So 40 over 10. That will take us 4 hours. If we take a bus, we can go 20 miles per hour. So it will take us 2 hours to get there. If we go by car, we can go 40 miles in an hour. So it's going to take us a single hour to do the trip. And then if we take a jetpack, we can go 80 miles in 1 hour. So it's only going to take us a half an hour to do the trip. So if you notice, as our speed is increasing, the time to travel the same distance will decrease. So if you think of our direct variation, when one doubled, the other doubled. When one tripled, the other tripled. When it cut in half, the other cut in half. Now if we consider when the speed is doubling from jogging to biking. If we look back, when we were jogging, it took us 8 hours. When we were biking, which doubled the time, doubled the speed, it halved the distance. So in this instance, when the speed doubles, the time gets cut in half. Same thing if you look at going 20 miles per hour to 40 miles per hour, the time doubles, but the speed gets cut in half. So same thing, it gets cut in half. If you reverse it and you look at starting at the speed being 20 and cut it in half to biking at 10 miles per hour, the speed is going to double. So it's doing the opposite effect. If the speed is divided in 4, so if we look at the jetpack, and then you divide the 80 miles per hour by 4, it's 20 miles per hour. The time it takes is going to get multiplied by 4. So there is this inverse relationship between the two. So based on this, does time depend on speed or speed depend on time? It's going to be the case that time depends on speed. So once you pick a speed, that determines how long the trip will take. So reverse of what we're used to time being the independent thing, but in this particular instance, the time is dependent upon the speed. Okay. So let's do our best to graph this. We're going to put the speed on the x-axis because that's our independent quantity, and we're going to put the time on the y-axis, which will be in hours. And the speed we have is in miles per hour. So let's plot all of our different points. Use a little bit bigger of a tool. If you walk at 1 mile per hour, it's going to take you 40 hours, make it a little smaller, to make this trip. 3 miles per hour, it's going to be 13.3, which is right around here. 5 miles per hour, it will take you 8 hours to make the trip. 10 miles per hour, you now take 4 hours to make the trip. 20 miles per hour takes you 2 hours. 40 miles per hour takes you 1 hour. So this is our graph. If we do our best to connect the dots, we have this inverse relationship. So you can see as speed is increasing, the time is decreasing to go that distance. Okay. So now if we want to estimate how long it would take to travel 40 miles at 7 miles per hour, we can go back to our graph. 7 miles is right around here. So it's going to take a little more than 5 hours. So we could say it's going to take about 6 hours. Or between 5 and 6 hours. If we want to make the trip in 2.5 hours, that's our time. So 2.5 is halfway in between. We'll see what speed that hits it at. And it's going to be roughly about 15 miles per hour. So we need to travel about 15 miles per hour to make this trip in 2.5 hours. Okay. So now let's find that equation that relates the speed to time for that 40-hour trip. So we've actually already done this. We know the distance is equal to the rate times time. So since the time is going to be the distance over the speed, or the rate, in our case, the time will equal 40 over our speed. So now if we have a particular car, maybe that can travel at 60 miles per hour, the time it would take to go this 40-mile trip would be 40 over 65. So it would be about 0.62 hours. And then you could convert that to minutes if you want, but if you did, this would be about 37 minutes. So just times it by 60. So this is exactly inverse variation. If we look at a comparison between these two, when something varies directly, as one increases, the other is increasing. So the algebraic formula we have is y is equal to some constant times x. So as y increases, x increases. So the quantity y varies directly with respect to x. In the other case, if you look graphically at inverse variation, as x is getting larger, y is getting smaller. as x gets larger in the other direction, y still gets smaller. Where here, as x got bigger in the opposite direction, y got bigger in the opposite direction. So algebraically, what we're going to have is now a constant divided by the variable x. So like the last example was 40 over x, you're going to have a constant divided. So it's the opposite relationship. So then you can see as one's increasing, the other decreases. So going back to these same type of examples, when we exchange currency, the value of currency you trade in varies directly with the amount you get back. So as the amount you trade increases, the amount you get back also increases. But in this other case, when you drive a certain distance, the time varies inversely with the speed. So if your speed increases, the time for the trip is actually going to decrease instead. So they have the opposite relationship. So let's try to write some examples. We're going to write an equation for a variation for the situation using k as our constant variation. So we don't know exactly what that constant is going to be. But we're told the price P at which a manufacturer is willing to sell a certain product varies inversely as the number of items that consumers are willing to buy U. So our price varies inversely, which means P is dependent upon the number of items, and it's inverse, so it has this form, the constant divided by U. Now, when a store has discounted gallons of milk by a certain amount, the total savings, T, varies directly as the number of gallons bought. So as the number of gallons increases, the total savings also increases. So T is our total savings. It varies directly with the number of gallons, G. So you multiply the constant by G. Isaac Newton discovered that the gravitational force between two bodies, F, varies inversely as the square of the distance between them. So this is a little bit different. It varies as the square of the distance. So my force varies inversely, which tells me I'm going to have a fraction and I'm going to have that constant above, but it varies with the square of the distance. So I don't just have a d here, I have the distance squared in the bottom. If it varied inversely for the cube of the distance, it would be d cubed in the bottom. So let's begin working with the gross pay for a certain hourly job. It's going to vary directly as the number of hours worked each. And we're going to use that fact to fill in the table. So I don't know the equation for this. I could come up with it, but I can just use my idea of varies directly. If one doubles, the other should double. If one triples, the other should triple. So I'm given for 5 hours, my pay is 56. If I double my hours to 10, my pay should also double. So the pay is doubling, and I should make $112 for 10 hours of work. For 15, my hours triples, so my pay should triple. So I should take 56 times 3, and I should get paid $168. From 5 to 20, my hours gets multiplied by 4, so the 56 also gets multiplied by 4. From 5 to 25, my pay gets multiplied by 5, or my hours gets multiplied by 5, so my pay should do the same thing. And I would make $280. Okay. But now, if I look at the number of days it takes for a construction crew to repave a certain road, we're told that varies inversely as the number of workers, W, that work on the project. So the more workers you have, the less number of days it's going to take. So it's going to have that opposite effect. So our baseline is that when we have 6 workers, it's going to take 30 days for the project. If I double my workers to 12, the number of days should get cut in half. So instead of multiplying by 2, I now divide by 2. So it should take me 15 days to do this project. When I triple the number of workers to 18, the number of days should get cut into 1/3. So we would take the original number, divide it by 3. It would take us 10 days with 18 workers. Likewise, we quadruple or multiply the number of workers by 4. It's going to make our number of days decrease by 1/4. So it's going to take 7.5 days to go through this project. And finally, if we multiply the number of workers by 5, we should divide the number of days by 5 by doing the opposite. So if we have 30 workers, it's instead going to take us 6 days. So in these instances before, I had a really nice way to get from one to the other. You multiplied by 2, multiplied by 3, multiplied by 4. But in the case you don't have a clear-cut multiplication, finding an equation is going to be a little bit easier. So let's consider the weight of an object on Mars. We're told that varies directly as its weight on Earth. So if we have a 170-pound astronaut set foot on the moon, they are actually going to weigh 64.6 pounds on Mars instead. So when you go into space, the gravity is going to be a lot less. So this 170-pound person actually ended up weighing 64.6 pounds on Mars. Because there's this direct variation, if I let m be the weight on the moon or weight on Mars, and I let's do w be the weight on Earth, we're told that the weight on Mars varies directly with the weight on Earth. So we want to find this constant K. And I'm going to utilize that I know a 170-pound person on Earth weighs 64.6 pounds on Mars. So this tells me my output is 64.6. This is a constant times 170. So to solve for the constant, we go ahead and divide by 170. And this tells us our constant K is going to equal 0.38. So our equation relating our weight on Mars and our weight on Earth is going to be m is equal to 0.38 times the weight on Earth. So now we can utilize this to talk about weight in different categories because I don't have a clear cut of how I got from 120 to 135. I don't know what multiplication that is. I can just go ahead and plug in the formula. So we're just going to take each of these weights and times it by the 0.38. So when you do that, a 125-pound person would weigh 45.6 pounds on Mars. A 135-pound person would weigh 51.3. 150-pound person would weigh 57. If you weigh 160 pounds, you would weigh 62.7. On Mars, 180 pounds would end up being 68.4. And then finally, if you weigh 195 pounds, you would weigh 74.1 pounds on Mars. Okay? So now we can answer some questions conceptually about this. Suppose in a second excursion to Mars, the landing craft holds an extra astronaut with more equipment, which makes it twice as heavy on launch than the first manned trip. How much heavier would this craft be when it actually lands on Mars? So it weighed one amount, we're doubling the weight, so when it's got direct variation, it's going to weigh double the weight on Mars. So it'll still be twice as heavy. On Mars because of that direct variation. On the trip after that, they get lightweight material that leads to the landing craft weighing 1/3 as much of the previous trip. So when it lands on Mars, it will weigh 1/3 of the amount. Now if we move to a different example that deals with inverse variation, we're told that as wheels roll along, the number of times it completes a full revolution to cover a certain distance varies inversely with the circumference of the wheel. So what that actually means is if you have a bigger wheel, the distance around the outside is going to be bigger than a smaller wheel. So when it rolls once, it's going to cover more distance in that time. So a larger wheel would roll less times to cover the same distance of a smaller wheel. So if we're told the wheels on my Explorer have a circumference of 240 centimeters and they make 150 revolutions to travel a certain distance, we can find that constant of variation. So remember, the rolls it takes varies inversely with the circumference. So let's call those R and C. R is the number of revolutions. C is going to be the circumference. And since they vary inversely, we have a constant divided by C. To find this constant, we're told that they make 150 revolutions when the constant, or when the circumference is 240. So this constant of variation would be 240 times 150. So the value of K will be 36,000. So an equation that relates the number of revolutions made by a wheel to its circumference in centimeters would be the number of rolls is 36,000 over their particular circumference. Okay. So let's use this equation to complete the table. So we've got R is equal to 36,000 over C. So I'm given all the different values of C. I want to take 36,000 and divide it by the circumference. So when you take 36,000 and divide it by 100, it's going to take you 360 revolutions to go that distance. When you have a wheel that's 150 centimeters in circumference, it's going to take you 240 revolutions. For 200, when you take 36,000 and divide it by 200, it will take you 180. For 250, you'll get 144. And then finally, when you have these large wheels that have a 300 centimeter circumference, it'll take you 120 revolutions to go that same difference. So if you notice what happens to the number of revolutions as the circumference triples, it gets divided by 3. When the number of, when the circumference is cut in half to go from 200 to 100, the number of revolutions is going to double. So it does the opposite effect. So these are those key differences between direct variation and inverse variation. So direct, they do the same thing. One doubles, the other doubles. Inverse, when one doubles, the other gets divided by 2. So it's the opposite or inverse effect.